Okay, yeah, so today is my great pleasure and honor to have our own Yuda Pearl to give talk in our CS 201 department seminar. I don't think Yuda need any introduction because he is so famous. When people talk about UCL computer science department, he is one of the top names. People will easily come up. So in short, Yuda is the winner of the ICM Island Turing Award in 2012 for his seminal work in probabilistic inference and causal reasoning. And he has recently written a book called The Book of Why, which is also one of my favorite books. And I think in today's talk, Yuda will also talk about some very basic ideas of causal inference from his book. So please join me in welcoming Yuda to give the talk.
It's a great honor for me to meet our colleagues and our students at UCLA. The reason for my talk is that we have been communicating for many years, and I always feel there is a screen between us. Many of us and many of my colleagues are working in data science, in the machine learning, in AI, and there's always a feeling on my side that we are not communicating with the same language. Then it dawned on me that we do have a new language to communicate with. And I would like to share with you what I mean by causal inference, and I use the logical perspective to share my thing, because it is the logic that connects us as computer scientists together. So I'll start with a picture which may be familiar to you. This is called the Agora of Athens. That's how it looks today. This is the cradle of democracy. It's the cradle of logic. And that is how it looks today to tourists, but this is how it looked in about the 4th century BC, when people or citizens of Athens gathered to communicate, or actually to argue about who can rule the city better. And that is the idea of democracy. And simultaneously with the development of democracy, there was a development in logic on the Euclidean geometry side. And some people even attribute the development of geometry and the craving of people for the simplicity and objectivity of geometry by the fact that they got sick and tired of arguing. Namely, the arguments get to the point where they were endless, pointless, and leading to something called demagoguery. And people craved for the idea of objective truth, which supposedly the axiomatic system of Euclidean geometry offers them objective truth. Aristotle was the first who came out with some questions about this connection. And he says, what distinguishes philosophy that we all love, like the love of wisdom, from demagoguery? The one that literally it stands for moving people or leading people. And he attributed it to the difference between truth and rhetoric. Then the question is, what distinguishes truth from rhetoric? And he came out with the word logic to the study of quest for objective truth. So logic, according to Aristotle, is the study of objective truth. Now the question is, what is truth and what is objective truth? And he came out with the astounding discovery that truth comes from out of form, not out of interpretation of the sentence. And this is something that we know from propositional logic. If one looks at a statement such as all Greeks are humans, all humans are mortal, therefore all Greeks are mortal, that will hold true regardless of how we interpret Greeks, human or mortal. For any A, B, and C, if all A's are B's, all B's are C's, then all A's are C's. What is then the secret of the forms that allow us to assign a truth value and believe in that inference, in that the truth comes from therefore, from all, from R, and not from the A, B, C, and D? That took quite few years to develop, the idea of formal logic, and it actually took 2,000 years until people came with a symbolic logic, with Boole and De Morgan in the 19th century. De Morgan, we all know De Morgan from De Morgan theorem, and we know Boole from Boolean algebra. But Boole published his pamphlet in 1847 at his own expense because he couldn't find a publisher. And De Morgan missed him by 1 year when he published his formal logic. And that gave a tremendous boost to Aristotle's syllogism and brought up formal logic. Well, according to that, I'm going 2,000 years ahead. And what is a valid inference? It's a question that Aristotle asked in his syllogism. And eventually we came out with the idea that the sentence or the syllogism, if premise 1 and premise 2, then conclusion is true whenever the conclusion holds in all worlds in which the premises do. So the key here is the idea of world and the idea that the left-hand side leads, or the conclusion holds in all worlds in which the premises hold. Okay? One can describe it in the form of a Venn diagram, but let's keep on reminding ourselves of the key issue of world. World is a truth value assignment to all propositions of interest. We know in proposition logic is just a truth table. Whatever is allowed, whatever is not allowed. So it's very simple. In probability, it's a probability table. And I'm going to convince you that there is such a idea of a world in causal logic. And that's what we're going to talk. So I'm going to slowly bring us up to the causal inference and see the relationship between propositional logic and causal logic. We can describe it in the form of a Venn diagram very simply. Here is the premise 1, here is the premise 2, and here is the conclusion. So in all worlds in which the premise hold and the premise 1 and premise 2 hold, it's true that the conclusion holds. And where are the worlds? The worlds are not dots. Imagine that you have here points. Okay? Each point assigns a truth value to premise 1, premise 2, and the conclusion. And as the world moves around, it doesn't matter how much they move, the point is still valid that whenever the premise 1 and premise 2 intersect, it assigns a truth value of 1 to the conclusion. That's the idea. And we can see how it is common to causal reasoning. We are going slowly and for purpose. Now, when I talk about causal reasoning, I have to tell you what are we talking about. We understand propositions, we understand probability, but what the hell is causal? Well, here it is. Causal inference, it is a logic and tools for answering causal questions instead of propositions. So give me example of causal question, and here are some examples. How effective is a given treatment in preventing a disease? What is the new tax break that caused our sales to go up? Or our marketing campaign caused? What is the annual healthcare cost attributed to obesity? These are all questions that came up and comes up again and again. You can read about it in the New York Times, in the Wall Street Journal. Whenever people are talking about attributing, preventing, causing this, especially nowadays, they're talking about discrimination, fairness in computer, fairness in machine learning. Okay? Can we prove employer guilty of sex discrimination on the basis of the record? And here's a personal decision. I'm about to quit my job. Will I regret it? Regret is another thing. What is special about those words that are marked, that are highlighted in yellow, is number one, I can recognize them 5 miles away. Number two, you cannot express them in propositional logic, nor in any other logic, nor in any language of science known to us. Why? They're inarticulable in the standard grammar of science because the standard grammar of science is bound to the symmetric symbol of equality. Y is equal to ax, the same as x equal to y over a. Whereas all these are non-symmetrical. And what happens is that all the equations of science, physics, astronomy, even social science, starts with the equality sign to be the measure or the dominating symbol, is dominating connective of our scientific language. And we are talking about asymmetry here. The atmospheric pressure causes the barometer to move, but not the other way around. You can move the barometer as much as you want, and you wouldn't affect the rain tomorrow. Now, it's all clear to you and me because we can fill in the asymmetry in our mind. But imagine a robot being put next to a barometer and looking at a 1,000,000,001 data points. The conclusion that may be drawn by our poor robot would be that if you move the barometer, yeah, you can affect the weather tomorrow. So this asymmetry, which we in computer science know as assignment symbol, is not in the general standard language of science. We have to supplement it with this asymmetry, and whatever I'm going to talk about today can be thought of as a calculus of assignment symbol. That's what I'm talking about. I can express all these terms in terms of an assignment symbol, but not in terms of equality. So let's continue and see what we can say about this assignment symbol. And we are going to look at it by comparing what standard inference of statistics looks like and the way that causal attributes come into the game. So in statistics, what is the oracle of all oracles? It is a joint distribution of observed variables. If you know that joint distribution, then you will have the answer to every probabilistic question about the domain. For instance, infer whether customers who bought product A would also buy product B. We have a symbol for that. The query is the probability, the conditional probability of B given A. That is given by the joint distribution if you had it. So I call it an oracle. It would give you the answer. Unfortunately, in most statistical problems, we do not have the joint distribution. Instead, we are waiting for the graciousness of the joint distribution to spit out data, and we look at the data and we're trying to infer the aspect of the joint distribution given by that, B given A. So here is an oracle that has been very, very helpful and admired by statisticians and by all of us who learn probability theory. If you had it, you don't have to do statistics. But what happens when you have a little, let's say, changes of a joint distribution? Like, for instance, estimate the probability that the customer who bought A would buy B if we were to double the price. Okay? So we are imposing a change on the environment and change on the mentality of the customers. We are presenting the customer with another price. Okay? Now we have a new joint distribution, that the one that prevails after we double the price. And who is responsible to tell us how P prime differ from P? We need to have an oracle to tell us this change. And the oracle I'm going to call data generating model. This is the new oracle. It is an invariant strategy by which nature assigns values to variables in the analysis. So we're looking at nature to be a society of listeners. Each variable, like the temperature of my eyeglasses today, is listening to the variables in the room and acts upon it depending on what he or she hears. That is the picture of the oracle. And this equation of motion in the room dictates how the answer to our question would be. What will be the eventual reaction of a customer to this change? So this is the scientific model of the world, which I'm going to adapt, and I believe most scientists will agree that this is a reasonable perception of reality. And now we are going to attribute to that oracle all the love and respect and that we did to the original joint distribution. It's a painful decrowning of a beloved oracle, because statisticians swear by joint distribution. This is the, I don't have any more words to express the reverence that the statisticians apply to joint distribution. This is let's say, the source of all wisdom, if we only had it. And instead now of finding aspects of the joint distribution, we are trying to find aspects of the data generating model. So here we have a new oracle, and the query is find certain aspects of the data generating model. Why? If it is a beloved oracle, it must be very complex, right? I'm going to show you that it's very simple. It's not complex. First of all, here it is. Formally, this is a bunch of variables. Each one listens to the other, but the key one is this one. For every variable, vi, there is a function, we don't know the function, it's a function that determines the value of vi according to what other variables are doing, the other variables in the domain, v and u. Some of them are endogenous, some are exogenous, depending on your choice and the scope of your domain. Good. So this is the key. Look at the simple one. Y is equal to alpha plus beta x plus ui. It's a typical, not regression, It's called structural equation, which tells you what nature does. Nature looks at x, multiplies by beta, add to it an alpha, also looks around if there is any factor uy that it should take into account, combines them and assign a value to y, assigns a value. And this is something we're all familiar with, right? It's called the structural equation. Economists started using it already in 1928, and it was invented by Sewell Wright, who was, he wasn't an economist, he was actually a geneticist, and it came to be known as a structural equation and path diagrams. It went through many gyrations, up and down. People understood it and misunderstood it, understood it again and misunderstood it. In my book of Why, I go through the gyration, ups and downs, how misunderstood it became in certain circles, in certain cultures, and then understood a bit and abandoned again, and so on and so on. It's a very strange kind of idea. It's not equality. This symbol really stands for assignment. Nature does all this exercise. You cannot invert it. You cannot say that x is equal to some constant times y plus other. No. So that caused the problem with statisticians and economists and social scientists and whoever you want, yeah, in understanding what it means. Today we understand what it means, and whatever I'm going to tell you now is going to be about the meaning of that structural equation, because I view nature to be a society of structural equations. Okay, let's look at example. A simple example: you wake up in the morning, you see the ground is wet, trying to find out what caused it. But never mind that. Let's just look at the connection among variables in this little domain of around your pavement. We have a sprinkler, which is normally connected to automatic device, which turn it on and off depending on the climate. You have a rain, which depends on the climate. You have a wetness. This is the structural model. This is the oracle. If you know all these functions, you wouldn't need to worry about any inference. That is a fully specified model, but we do not know those functions. And our question is, what can we say still? Well, it's a collection of springs because you have ropes behind the data. If you just look at the data, you'll see a collection, two photopools, CSRW, CSRW, 1, 2, 1 day, second day, a day after, but you don't see the ropes behind the data. And that's the secret of causal reasoning, the ropes behind the data. What can you say about it? Well, I just to assure you that I'm dealing not only with toy problems, such as sprinklers and pavement. This is what economists do when they're trying to find the relationship between price and demand, income and wages. Here you have a cycle. So what? We have a cycle. And so just I made my point. It is a workhorse for economy, for economists. Let's see what kind of question should the oracle answer. First, we want the oracle to answer observational question. What if I see? What if I see that it is the sprinkler is on? What can I conclude? I can conclude perhaps it's summer. Next, I want the oracle to answer action questions. What if I turn the sprinkler on? I also want him to give explanation. So to ask, what if we did things differently? Or what if it wasn't raining? Or what if What if the sprinkler had not been on? Go back in time. And if we want to keep, also we want the oracle to decorate the answers with probabilities. But that's a simple technical problem that we can all do nicely once we have answers to the basic question. It turns out that these questions have signatures, syntactic signature. First, we have a name for that in English. What is, what if, and why? And then we have syntactic signature to it. I'll show you here. They call it what is give the probability of outcome Y given A. This is the famous Bayesian conditioning bar. Straight probability, no problem. Here there is a new symbol, do A, because what if I turn the sprinkler on despite the fact that it is winter? And here is a new symbol, subscript. What would be the value of Y had A been small a, given that in reality A is equal to something else? It forms a causal hierarchy in the sense that you cannot answer question in a certain level unless you have information or data given from this level or higher. I should say lower, but higher, we'll see it. And I describe it nicely in the book of why in terms of development, in relation to development of human intellect. In statistics, we have the owls and the snakes, which have developed a very nice and sharp vision system of prediction of where the prey is going to be a minute later. We have a robot today doing beautiful machine learning, and at that level, mostly in associational level. Above that, you have interventional level. What if I doing in intervening? Here we have a development of tools, and the child learning in the crib learn what will happen if I rattle this toy or rattle that, and so on. And on top, we have the highest possible level that I can think of. It's counterfactual, imagining, retrospective understanding. I don't have any more fancy words to decorate it with. So that here we want to see the development, the imagination and the creativity of scientific thinking. And the aim is to have an automated scientist deciding on what experiment to run next, what variables to measure, and so on. What hypothesis to generate, to test. So all this comes at the highest level. Okay, let's leave the book of why for a second and go back to the nitty-gritty of seeing how you can answer those questions. Here's the deriving effect of actions. I ask, would the pavement be wet if we turn the sprinkler on? I'm going to apply my muscles now, and I'm going to turn this sprinkler on, which means the variable S for sprinkler is not going to be a function of the climate and whatever noise is determining the sprinkler on and off. It's going to be enslaved to my muscles, to my hand. How do I express it? Very simply. I just simulate it on this model. I take this knife and I cut off the connection that previously affected the variable sprinkler, and I subject it to the force of my muscle and set S to 1. Sprinkler is on. What do I have now? I have a new structural equation, with a set of structural equations, with one equation replaced by a constant. Big deal, we all know how to solve equations, so we solve it. And the answers we get will be an assignment of value to W under this condition. So I call it find if W is equal to 1. That's a question, right? In a mutilated model in which we replaced the variable, should be here with S, X by small x. It should be really the variable replaced the variable S by 1. It's a mutilated model which had a subscript here. Good. What else can we do? Deriving counterfactual from a model. I can do the same if I ask the question, would the pavement be wet had the rain been on? Currently, we see the rain is perhaps, even we don't see the rain, we do see the rain is off. Okay? And now we imagine that some hidden word turns the rain on. Okay? Would the pavement be wet? The answer is the same. Just find if W is 1 in the mutilated model where the variable R received the value 1. Good. I can say more things. I can say, suppose I see that the pavement is wet. Right? What if the rain was off or something like that? I have to go and if I see something, especially in the consequence, I have to go back and update all the U's which are responsible for what I see, and then do the correction, and then do the mutilation and intervening, and then ask the question. Good, but it's still solving equation. So that is the beauty of counterfactual. It is extremely and embarrassingly simple. Every counterfactual has a value in M because I can do this mutilation for every variable that I want, and conclusion is we have an oracle for counterfactual. I call it even the law, the first law of causal reasoning. At some point, I call it that way. The law of counterfactual. Summarize the value, the counterfactual. Y had x been small x in situation U is nothing else but the value of y in the mutilated model in the situation U. Here you see it graphically. Here I have the original model. I do the mutilation here. I set x to small x, and I hear what the solution is going to be called y sub x. The value of y had x been small x. Easy. Counterfactuals are embarrassingly simple, because any high school kid that can solve equations can find the value of any counterfactual you can think of. Assign a truth value to every counterfactual you can think of. Okay? Had Cleopatra had a bigger nose, had Hillary won the election, if you have a model, of course. I'm not saying I can tell you what would happen to our politics had Hillary won the election, but I can tell you that what I need, what kind of model I need to be able to assign truth value to that counterfactual. Okay. Now I want to first, before we go into the inference engine, I want to first to convince you that data is insufficient for going from level 1 association to level 2, which is intervention. And I do it without any numbers, just by showing you pictures. Here is a diagram, it's called the scatter diagram, of points and data points, right? Connecting cholesterol to exercises. So it seems like the more you exercise, the larger is your cholesterol level. We all know it conflicts with what we understand that this relationship. And indeed, it can be obtained if you don't pay attention to the age group. In every age group, you find the opposite relationship. Okay? The more you exercise, the less cholesterol you have. Now, this is not my point. Everybody knows that. Okay? My point is that you cannot tell ahead of time what kind of variable will dictate the correct answer. For a certain variable, you should look into the collapsed scatter diagram. In other variables, it is the disaggregated, disassembled, conditioned diagram that gives you the correct result. And you cannot tell the difference unless you know the story behind the data, which means the data itself cannot tell you which diagram to look at. That is the point of the Simpson paradox. And this already constitutes a qualitative proof that everybody can see that you cannot go from the level of data, statistics, to the level of intervened engine that's ranked the ladder number 2 without the story behind the data, the story behind the data generating model. Okay, I hope you are convinced by this picture. Some statisticians are still not convinced. So I'm telling you that if you don't see the point, you're not alone. Okay, now we're going from oracles to inference engine. Who needs an inference if you have an oracle? Right? Unfortunately, we don't have a completely specified model. Those functions that you saw on the right are not specified. All you have is the relationship between the arguments. Which variable is an argument from what other variable, not the function themselves. So we have a question here, a query, and we have a model that can answer it. It's a face of reality, but we only have a partial model. For instance, we might only have the graph, or we might have only a bunch of assumptions about them. All of them are features of M. Okay. And if we have them, the question is, can we combine it with data and get to turn the crank and get the engine going and find a calculus that will give you the solution that you are asking for. And the problem is said to be solvable if any model permit the calculus to express the query in terms of the available data. So you present the oracle with the kind of data that you have. It may be experimental, it may be observational, it may come from a badly conducted experiment. Once you specify how badly it was conducted, and you want to bring all this information to bear, you want to calculus to turn the crank and give you an answer. It gives you an answer in 2 stages. First, it might tell you you don't have enough assumptions, which means you cannot find a solution or an estimate to the query. And if it tells you it cannot be done, it means it cannot be done by any method. That the assumption that you have and the data are not sufficient to give you an answer. And if it can, you want the calculus to tell you how. This is what I'm trying to do. It's the same sort of idea that we had in propositional calculus. But here we have 2 kinds of inputs, not premise 1 and premise 2 and conclusion. We have assumptions about reality, and we have data from various sources, and we want to find an answer to the query. Okay? And the query will be said to be answerable if it so happens that the intersection, the combination of assumptions and data specify a unique answer to the query. And where are the oracles? In all oracles, each point here, instead of being a truth table, it's now an oracle, namely, it is a fully specified ascription of functions to the edges of the graph. So each point here is a fully specified structural equation model. It's the same picture. But now all we have to do is to build the calculus in order to give us to answer this question. Is it solvable or not? I can do it if I have another law. One law we have already. It's the law of counterfactual. Every structural equation assigns a truth value to every counterfactual. I need a second law. Here is the first. Second law is the law of conditional independence. Okay? People who took Adnan class in Bayesian network know it because it's the law by which we determine if things are conditionally independent in the graph. Okay? What it tells you is the following. If you look at the graph, if you see separation between x and y, it can be sets, okay? In the graph, it implies that you have conditional independent in the probability or in the data. Okay? Separation in the model implies independence in the distribution. And that's very powerful. Why it's powerful? Look what we can do with it. Okay? It tells you each function, no, despite the fact, first of all, it's a miracle. Okay? Because despite the fact that each function can be made up of millions of microprocessors, despite the fact that these are crazy functions, could be continuous, it could be discrete, despite the fact that these u's, which are factors, exogenous variables, can be of any possible distributions unknown to us. Okay? So it's independent on the function form and independent on the distribution form of these. Whether or not you have conditional independence in the distribution, in the data, is determined by the graph only. So that is a beautiful, powerful thing. What can you do with it? First of all, how you use it. Each missing arrow, which you find here, advertise independency in the data, conditional on the separating set. For instance, here you have missing arrow between the climate and the wetness, and it advertises a conditional independence in the data, C independent on W, given S and R. Beautiful. Another one is missing between S and R. It advertises conditional independence of S and R, given C, not W, for a reason that I will skip now. And what can you do with it? Look at the application. First, I can do model testing. If one of those advertised conditional independence is violated in the data, I can say that my model is wrong. I can say even more. I can even find and learn the structure of the model by keeping track of all the observed conditional independency and ask, is there a set of graphs which are compatible with my data? Perhaps I can find a parsimonious description of this set, and perhaps my query can be answered with yes or no, regarding of the membership, and regarding of the, in all set, in all members of the equivalent set. Okay? That would be nice. Then we can do reduce. What if we do a question about intervention, reduce them to symbolic calculus? And this is what happens with the do calculus, and I will show you how it's done. I want to find out what the effect of x on y is. Why can't I do it by simply look at the correlation between x and y? Because it is confounded by spurious paths here. So what do I do by intervening? I cut off these links, which previously determined the how x varies with its parent, z3 and z4, and I establish a constant, and I force x to be a constant. This is what I do by physical intervention, but I can simulate it using conditioning. I can simulate it by a symbolic operation on the model, still cutting off all the spurious path. Here is a way of cutting them off. If I condition on Z1 and Z4, I simulate the action of blocking all the path, all the spurious path. This comes from the DESEPARATION. DESEPARATION tells you that conditioning on Z1 and Z4, all spurious paths, you can see here, will be cut off, will be blocked. Beautiful. I have another set. I can also condition on Z4 and Z5. And in general, you give me a graph, I can tell you which set thou shalt condition on in order to cut off all confounders and get a simulation, an emulation of the intervention. And this brought up it's called backdoor criterion, which is used to determine what you should condition on. It also tells you how. If you condition on this set Z, and you take the weighted average of the ordinary conditional probability of the outcome given X and Z, weighted by the prior probability of Z, that will give you an answer to your query as if you had intervened on X. So it's powerful in this sense, but we can go more than that. Is it only adjustment? Is the only means that you have to get answer to your intervening question? No, I can go further and I say, for instance, if I want the effect of smoking on cancer, there is no path that I can cut off now. This purest path is created by an unobserved genotype, which make people crave for smoking and be at cancer risk. So, but there's no way for me to find a variable upon which I can intervene, which I can adjust for that will block this path. It's all made up of unseen, unobserved variables. But I have an intermediate variable here, tar. Can I use that measurement of the tar deposits to find out the effect of smoking on cancer? Well, look what we want to do here. We want to have a query which has a do in it, and we want an answer in terms of the joint probability of S, T, and C, okay, without any do. So we need a calculus that will take away the do and convert it into ordinary probability expression. It is available, and I can show you how it works. Here is my query. Find the probability of cancer, given that you do smoke, okay? And I turn the rules of the do calculus one by one. I'll tell you the rules later. And slowly, I can convert the expression into something that answers my desired format. You got a probability distribution consisting of no do operator, only conditional probability, and this is the answer to my query. Yes, I can do it. And what are these rules? These are names of rules of the do calculus that I'll show you later, which gives you a license. If the graph satisfies these conditions, you are allowed to go and make this transformation, one by one. Here are the rules of do calculus. These green conditions are the licenses that the graph needs to tell you to permit and to legitimize the transformation. Here's the transformation which allows you to ignore an observation. Here's the transformation which allows you to ignore an action. And here's an action. And here it's a combination, converting action to observation. Good. So we have a calculus. Now let's look at the inference engine. What is the input and output for the inference engine? Well, the input is what you have. You have a query. Tell me, what would be the effect of inoculation on typhoid. And that's a query. It's an expression in the language of causal calculus, the effect of something on it. It's only an example. I can have a query in the form of counterfactual. What if Cleopatra had a different nose? Here are the assumptions. Assumptions are given to you in a form, normally in the form of graphical model, but could be more. Like if you have some idea about the form of the function, like if they were monotonic or they were smooth, you can allow those assumptions to be in the game here too. And here is the kind of data that you have, you can bring to bear. And now you turn the crank and you let the engine produce the answer for you. What answer are you asking for? First of all, as demand, is it possible to express the query given the assumption? And it's a recipe for answering the query for any data. So to get this estimand, you don't need the data. Once you got it and the answer is yes, then you estimate it using the best tricks of machine learning. And then you also can answer the question of to what degree does the answer corroborated with the data? And to what degree does the model compatible with the data? Okay, here's how it works in real life for a simple question, the simple one that I showed you before. You have a query, what's the probability of the outcome given that I do X? And you have assumption in the form of a graph. Here the Z is a confounder between X and Y. You give it to the engine, and the engine turn the crank, do calculus, and gives you, yes, you can do it. You have enough assumption. All you need to do is to take the conditional probability there, weight by the prior probability of the sum, and you will get the answer. So you have a recipe here of how to handle data before the data comes on. Now you turn the data on. Bing, zoop, provide the answer and give the actual estimate to the query. Namely, this is where machine learning comes in. You take finite samples and try to find an estimate of these probabilistic expression. Going from finite sample to distributional expression, that is the role of machine learning. And then you can also answer to what degree it is falsifiable and so on. I will go forward. Oh, I reached the first part of my lecture. I hope I have still a few minutes left, because here I want to tell you the accomplishments of this fancy inference engine and what it can do. Here are the tools that have been achieved by this calculus. First, encoding causal assumption in transparent and testable way, and don't knock it. This is one of the most important accomplishments here. If you have assumptions, you can articulate them, and you can communicate with your peers, and you can argue about them. You can only do it if you have a language to express your assumptions, and the language did not exist before we had the language of assignment. You can predict the effect of action and policies as we saw. You can compute counterfactual. And don't think that counterfactual are just something metaphysical. They are important for asking question of attribution, explanation, susceptibility, fairness. It's all driven by the idea of counterfactuals. I'll show you example of attribution and explanation. Tool 4, to separate direct from indirect effect, also called mediation. And this is also very important. That's the distinction between being fair or unfair. inequality and discrimination. Tool 5, robustness or domain adaptation, transfer learning, and so on, which many machine learning, many, as you said, generations of machine learning have been bothered by or unable to solve because the solution does not exist in the realm of data. The solution exists in the realm of a combination of assumptions about reality and data. Tool number 6, recovering from missing data. Tool number 7, causal discovery, which has picked up momentum in the past 2 years. And I'll just demonstrate it quickly that we saw already. It's in the literature. Find the effect of warm-up on injury, tells you which variables should condition on, which you should not condition on, even previous injury should not condition, and answer the question that sports physicians are still unable to solve, namely whether warm-up exercise contribute to injury or minimizes injury. And I summarize this section of intervention by stating a general theorem here, that every expression, look at that expression, the query, find the probability of a set of variables, given that you act on a certain variables, and given that you simultaneously observe other variables. So you have here, we call it conditional action. The effect of action conditional on certain observation. Okay? This can be decided in polynomial time. Moreover, if Q is estimable, then its estimate can be derived in polynomial time. So the decision problem is polynomial, and the actual production of the estimate is polynomial time. And the algorithm is complete in the sense that if it tells you no, then no other techniques in the world can give you an answer. So you cannot use terms such as, oh, this is true for DAGs and not true. No, it is unavailable with the assumption that you have. And finally, the same applies to the effect of treatment on the treated, which is really a counterfactual term. Never mind. Okay, let's go forward. Algorithmization of counterfactual and the corollaries. The corollary that I want to focus on is the last one. Causes of effect as opposed to effect of causes. Attribution is one example. What can we attribute guilt or responsibility to a certain event or to a certain action, given the outcome of that action? The cause, what is the cause of a given effect? Example is, Your Honor, my client, Mr. A, died because he used this drug. I would like the drug manufacturer to pay compensation to his family because he would have been alive otherwise. So that according to the court of law, not my invention, a court is to decide if it is more probable than not that Mr. A would be alive but for the drug. So here you have a combination of probabilistic expression, more probable than not, embedded with but for, which is a counterfactual. If you try to write it in a probabilistic expression, you get into impossibility because you have to find the probability that he is alive, given that he's actually dead. Okay? What's the probability he would be alive had he not taken the drug? So you use here the counterfactual, the subscript for the predicate, for the antecedent. And the court would decide on a compensation if it is greater than 50%. We call it probability of necessity, but for. Under certain conditions, you can find a bound on this probability of necessity. And if the bound is 1, you definitely the jury should proclaim the defendant guilty. And the nice thing about it is that if you combine experimental data with observational studies, you can get more, and narrowing the bound, more than each study alone. So this combination of experimental and observational data gives you narrow bound that you can use in life, in real applications. And one of the applications that came up recently was with respect to the COVID pandemic. The question came out, what are the patients that are in greatest need? Okay. These are patients that are susceptible to treatment. Then the patient, what are the patient characteristics C will improve if and only if treated. Look how I write it, probability of necessary and sufficiency, which means given that the patient has characteristic C, what is the probability that he will be cured if he takes the treatment? Argument one, and he would die if had he not taken the treatment. It's a counterfactual expression. You cannot express it in terms of probability, nor can you get it from experimental data. So you need both. Experimental and observational studies provide informative bound on that. And we have now, and it's in general. Whenever you go from group data to individual behavior, it requires counterfactual logic. So all the talk about personalized medicine are, I would say, deceptive, unless the people behind them know about counterfactual logic and the techniques that we have to narrow the bound and getting operational answers to questions such as the susceptibility of patients and to what degree they can be properly treated. Tool number 4, mediation analysis, the distinction between direct and indirect effect, which is important for question of fairness. Why do I say that? Because this is already the result, but here is the question, can the employee be declared guilty of hiring discrimination just looking at the data, at the employment record? Okay, here we are punishing a guy for discriminating in hiring based on gender, even though this link, that qualification can be gender dependent. The employer is not responsible for society's ill that makes women or men less or more qualified for the job. The employer is responsible only for this link. Okay, so what is the direct effect of X on Y? Well, spontaneously, I would like to say condition on M. Then you break this indirect loop, and all you have is the direct one. Wrong, because he adjusts for M, and the answer is no, because there could be some hidden unobserved variable which confounds Y and M. Right? So if you condition on M here, we are going to get into the mediation fallacy. We create a confounder, and it won't give you the correct result. So the answer could be perhaps not condition on M, but find the expression for the control direct effect, namely do X1, do X, and do M. And we know how to do it, right? Because we have an answer to every expression which involves do's. Any combination of do's and observation can be identified. It's still not perfect because the law has a different notion of what constitutes the lawmakers have a different notion of what constitutes a discrimination. They say that the employment case, the question would be whether the employer would have taken the same action had the employee been of different race or age or sex and so on, and everything else had been the same. You see here a combination of counterfactual is actually nested counterfactual, and he's talking about the individual here, not about the population, but the individual. So you just take the way that lawmakers talk and the way they write and justify their definition of discrimination, and you translate into a counterfactual expression. We know how to do that. So here you find the nested counterfactual. What is the direct effect of x on y? With the expected change of y when we change x from 0 to 1 for each individual, and we keep m, the mediator, constant at whatever level it attained before the change. It's a nested counterfactual, but are we scared of nestedness? No, because counterfactual is nothing else by solving equations. So we solve them twice. Bing, bang. First we solve them for x0, then we solve them for x1, and we nested it. Good. We have an expression. Once you have an expression, wow, you can bring to bear all the power of the inference engine and ask, can I identify it? Under what condition can I or cannot? That is the end. Okay? Noted, yeah? Okay? And we go to the next tool. The next tool that I want to brag about is the generability and data fusion. Everybody is concerned with generalizability because science is all about generalizing from a laboratory to the field. You conduct experiment of mice and you want to generalize it to human beings. You have data taken under certain conditions in the cockpit, and you want the same data to work in the battlefield. So generalization is extremely important. And I would say the generation of machine learning have been battling with the idea that things do not generalize. They even invented names to that. They called it domain adaptation and machine and learning. Well, I forgot the word now. Uh, I'll get to it. Okay? It cannot be done. It cannot be done unless you have picture of reality, unless you have ability to understand the commonality between the population or the environment you have now and the environment for which you want to apply the conclusion. You have to understand what are the common features of the two and what are the commonalities, what are the differences, the diversity between the two on a causal level, not on the superficial probability level. So the fact that you have a different probability in the training set than you have in the target population doesn't give you enough information of how and whether it is possible to generalize. You need the difference on the level of causal effects. Here's an example of what you can do, or what you want to do. Ideally, you have data coming from various hospitals, taken under different conditions, under different populations, and you want to ask a question about a totally different location, Arkansas, whether only a survey data is available. You want to combine all this information and assign a value to the causal effect of X and Y in the population of Arkansas. On this level of discourse, nothing can be done because it is not formalized. Okay? But once you reduce it to a graph formulation and understand the commonalities and differences between the various environments and the commonalities and differences in the conditions the data was taken. Here you find a missing link, which means it was experimental study. Here you find this link inserted, which means it was observational studies. And here you have the differences, where the difference lies, whether it lies in Z, in S, and so forth. Once you have it formalized in that way, you can combine it and get an answer, yes or no. If no, then no one else can do better. It's completeness result. And that's why I'm putting down the completeness so importantly, so important, because completeness tells you that you are not just getting a negative result because you're using DAGs and you're not using another formalism. No, because your assumptions are insufficient and no one else can get better result given the same assumptions. Okay, so fusion and externalization studies can be determined once the commonalities and differences are encoded in diagrams. When fusion is feasible, then the fusion formula can be derived in polynomial time, and here's the important part, the algorithms are complete. Therefore, it tells us when transfer learning, that was my missing keyword, transfer learning and domain adaptation are feasible and how. And that's something which is missing from the work I see in machine learning. What should hold true in the world so that my algorithm will give me what I want? You need this anchor to reality which is outside the data. I'll go into tool 6 and 7 quickly. Tool 6 is fine. You have a data corrupted by noise, by missingness. What does it mean? There's some entries in a table are declared M, missing. The subject did not fill in the entry here, or the patient forgot the severity of the accident, or whatever pieces from the scenario is missing here. So you mark it with M. Now, given that kind of table, you want to find out, to ask question. What's the average, what the conditional probability? Or what is, no, sorry. One typical question is what the conditional probability of X on Z had data not been missing? That is a question. And here I see, if you express it in graph, in which you express the reason for missingness, here is a proxy variable Z, which tells you that something is missing. Here's RZ, tells you something is missing in variable Z, and you find out the reason why it's missing, maybe two other variables, and how they are connected together in a graph. Once you have the reason, then you can answer it. Is it possible to estimate what I want to be estimated or not? And if yes, give me the answer. Give me a procedure by which I can work on this table and find out the conditional probability on X, on Y, had data not been missing. So I'll summarize it by saying that the result is a graphical criterion unveil when estimability is possible, when it is not, and how. And interesting, missing data is a causal problem. It's not statistical problem. It's one of those discoveries that was shocking to us and say, and because we still believe that many of so-called statistical problems are really causal problem in disguise. I'll go quickly over tool 7 because you can read about it in the literature and it's been picked up in momentum in the past 2 years. And it is a new work now by Benjo on finding out the models, the causal models using invariance. And I just want to summarize it with 5 lessons from the theater of causal inference. I'll go to 5 more, and then I'll let you ask the questions. The 5 lessons is number 1, every causal inference task must rely on judgmental extra data assumptions. We have ways of encoding those assumptions mathematically, parsimoniously, and derive answers to questions of interest. We have the mathematical machinery to take those assumptions and derive the question of interest. And we have ways of doing 2 and 3 in a language that permits us to judge the scientific plausibility of our assumption and to derive their ramification swiftly and transparently. Besides, it's also fun and easy. And what key insight I really would like my colleagues and all the students that want to study machine learning and data science. Data science is a two-body problem. It's connecting data and reality. And reality includes the forces behind the data. You cannot exclude them from the consideration. Thinking about data science this way behooves you also to understand that data science is the art of interpreting reality in light of data, not a mirror through which that data sees itself from different angles in the mirror. This is what I see being done again and again in machine learning, and it doesn't lead and doesn't give you any answer to the often asked questions of explainability, of transferability, and these are all dead ends unless you look at data science as a two-body problem. I'm about to conclude with one quote from Einstein. Who can finish a lecture without quoting Einstein? The development of Western science is based on 2 great achievements: the invention of the formal logical system in Euclidean geometry by Greek philosophers, and the discovery of the possibility to find out causal relationship by systematic experiment during the Renaissance. Perhaps Einstein would have added a 3rd one, the ability of data science to quickly discover, to fit data, okay, efficiently from finite samples. Okay. But still, you cannot give up on the first part, which is the formal logical system invented by Euclidean geometry. It represents reality as one of the elements, one of the components of data science. Here I'm about to finish and to thank all my co-authors and co-principal investigators and former students, and also take a break for quick commercial. You can get all the answers to all your questions in this little book. Okay. End of slide. Good.
Hey, thank you, Yuda, for the great talk. It's so inspiring. So I think now it's time to take a few questions. I see someone raising hand. Let me. Okay. So Sammy, you can, go ahead to speak.
So I stopped seeing. Oh, here I see myself. Yeah.
Yeah. So I will unmute them, and they will ask your questions. Yeah. Hi, Kaiyang. You can just unmute yourself and speak and ask a question. Mm-hmm.
Thank you very much, Professor. I have a question. So, if right now a lot of fields in, especially in medicine, when you find out the optimal solution, let's say through a randomized trial or through causal inference problem methods, you would just take this optimal path or drug, and ethics would not allow you to take any other paths. So do you think eventually we'll converge to like an optimal path in terms of what we use as a policy, and that would limit the exploration and the use of like finding new knowledge through causal inference? Maybe this is more philosophical.
If I understood your question correctly, you're asking what if we have some ethical restrictions on certain drugs or on certain people taking certain drugs. I have no answer if we have that kind of restrictions. All I can tell you is we have to model those restrictions and get and express our query clearly. And the calculus will deliver to you the answer, whether your assumptions and the restrictions are sufficient for getting the results that you hope to get. That's all mathematics can deliver to you.
Thank you.
Hi, Paul, you can ask the question. Yeah, you can just unmute yourself.
Oh, I have a sort of perhaps a silly question. We have a big problem nowadays with kind of pseudoscience, or people having the illusion of entertaining the illusion of causality or the illusion of control where there really isn't any, right? And I'm wondering if you have sort of insight on how to deal with this enormous problem of people ascribing too much causality in a way that can be understood by ordinary people.
Interesting question, because it has to do with the public perception of various advertisements and various communication modes by the media, by the journal, by the press. The reason that causality is so badly understood is because we are all experts in cause-effect relationship. It's embedded in our mind, in our neural net, if you want. So because we are experts in cause-effect relationship, we jumped to conclusion very quickly, because even if we see just correlation, we immediately give it causal interpretation. It's part of our nature. I should say we evolved that way, because who cares about correlation? We want to take action and find out if we can catch the mouse here or there. We have to be able to act in the world. So evolution has programmed us with that kind of bias. How to correct for it? We have analysis, and all we can do is to educate the public. And I think the machine learning industry has done a bad job in terms of this aspect of education, because it's given people the notion that all wisdom resides in the data. And therefore, just you have to mine deeper and deeper and deeper, and eventually you're going to get an answer to your question, even if your question lies on different levels of the hierarchy. So in that, if you're taking this into account, it has been destructive. But now that we understand the balance and what data science stands for, it's time to correct for that. And we have all the means of correcting for that. We have a calculus for action, which is different than the calculus of seeing. Okay? We can have a calculus of blaming, of regretting. It's a counterfactual. I think we have now the tools to explain to the public the differences and how to treat each published story correctly.
Hi, Professor. So in the last 2 to 3 decades, we have established identifiability for like various sets of questions, and we also like have solved those questions along with the completeness results. So my question on a basic level is like where to take it for the future in the next 1 or 2 decades, meaning what are some of the most important and challenging questions that would be the evolution of what we have done so far.
So you ask me what I'm going to work on the next 5 years? I can tell you where my interest lies. I think this oracle that we talked about is the first computational model of understanding, of deep understanding. And therefore, it is a great computational model for multi-agent work. Communication among agents could be conducted effectively with this oracle, which is really a structural equation model, right? Well, we can program now algorithms that will answer question, what does my colleague believe in? What can I do in order to change his or her belief? And when we have communication among multi-agents, we have a tremendous power here. And in addition to that, we can introduce utility, and we can introduce question about free will. Does my colleague act from his own free will, or is he subject to pressures and so on? This will be a tremendous advantage to teamwork, like robots playing soccer. Whether we should program them with the illusion of free will, and so they can communicate better and play better, and be able to blame each other. You should have passed the ball, and so on. Whether this kind of illusion would result in overall better team performance. So this is what I want to spend my time on, the multi-agent system.
Thank you.
Dr. Pearl, thank you for the great talk. I had a question about, it goes, GPT-3 seems to play well with many real-world concepts despite not having a causal model of the world. Do you believe neural networks could be augmented with your tools to perform causal discovery and causal reasoning implicitly?
You asked me several questions. Some of them, the answer is no, some of them are yes. Causal discovery, yes, there is a potential there. We still don't know how great the potential is, but we have a means of quantifying it because we have a way of answering the question, what should be the world like? What should be reality like in order for those algorithms to succeed? That is a question that could not have been answered by looking at the data only. You need the outside observer, the anchor in reality to be able to answer it. So it's gonna be answered in the next 1, 2, maybe 5 years. That's for causal discovery. Now, in terms of discovering cause effect without the causal discovery, the answer is no. No, I don't know how GP3 or GP12 plays. I know that it's impossible to go from level 1 to level 2 of the ladder just by looking at data, no matter how smart you are. It's just undoable.
Thank you.
Dear Professor, thank you for your talk. And my question would be, how do you see we could connect causality framework and signal processing? Because currently, from the talk, it seems that the model is given all the variables already. Those are abstract variables like the rains or the thermometer. But we have to determine the variable from the in the first step. How do we determine, say, like the thermometer from raw visual signal? Could we combine causality framework in some way? Thank you.
I know that the question of defining variable is very important. But in the signal processing world, you have measurements. Those determine the variables. The deflection of the barometer determines the variable called deflection of barometer. The availability of a device called barometer determines what we mean by deflection of barometer. We have a measurement of an independent measurement of the atmospheric pressure. That is another variable. So I think in the signal processing world, if I'm not mistaken, I should go back to my engineering days in the Technion, whether the question of defining the variables has been important. I know, however, that in abstract, yes, it's very important. If I allow myself to define new variables in a crazy way, like I take, for instance, the pressure and the logarithm of the temperature and combine it by the hyperbolic R tangent of the gravity, and that is a meaningless kind of variable, and I screw up all my variables in terms of those screwy ones, I get ridiculous results. So there is something to the variables which are naturally presented to us by our available instruments. Oh, the typical answer to that is the Gru and the Blin in the philosophy of science. You're familiar with it. The sky will be blue tomorrow because it's always been blue, but not true. It's always been Blin, and it's going to be green tomorrow. Why? Because green is defined as everything which was blue up to today and turn green tomorrow. So you can screw up the variable and define new variable and get ridiculous results. I agree with it, but I don't know if the practice of signal processes is so sensitive to this question of a choice of variable, given that we are bound with our measuring devices.
Okay, thank you.
Thank you. So we also have some questions in Q&A. I think some of them are clarification questions. So Yoda, do you want to answer these questions in the Q&A?
What is the question about the questions?
Okay, so the first question is about the drug example, the counterfactual example you give in your slides. So the question is, what is U in that example? So there's a variable U.
What is U? That's a very good question. Yeah.
Mm-hmm.
U is a situation, or you can be an individual, a unit. Is whatever information needs to be brought to bear in order to make those functions deterministic. So you could be an individual, because the individual, once you know the individual and the anatomy of all the veins and arteries, then you can answer all the questions here deterministically. So you just say, you is Mr. A, an individual. Or you can be a collection of unknown variables. But had you known them, you can answer all the questions deterministically. That's the definition of a unit. It could be a situation, right? Right now, this particular accident, what is the cause of this particular accident, given everything that we know about it, okay? The outcome, okay? The factors that we have observed, and any question about the individual situation and individual accident constitute a unit.
I see. Thank you. Yeah, that's a very clear. And another question from audience is about, I think it's a more general question. So the question is, would you see the value of causal reasoning for practical reasoning, in particular to design goal-oriented intelligent agents? For example, there are some agents aim to achieve certain goal. I assume, for example, is a, conjoint certification agent or something like that. So the question is whether causal reasoning can be used in this kind of agent.
I don't know what kind of reasoning, what other kind of reasoning could be used. It must be causal reasoning. If I want to motivate the next agent, I have to know what motivates I have a causal model of his or her motivation. So obviously it must be causal, right? Now we have a machinery to do that, to articulate it, to make all the assumptions, and to implement it in a calculus. So of course, I don't see how anyone can talk about multi-agent system without having computational model of the understanding. And understanding means causal understanding of how the agent understands the world. And my definition of understanding the world means being able to answer questions on all three levels of the hierarchy.
See, thanks. Yeah, I think in the interest of time, maybe let's take 2 more questions. So I see someone raise hand. Please go ahead to ask a question.
Thank you for the great talk, Dr. Pearl. My name is Aishni. I'm a first-year master's student, and I have a question about the level 3 in the ladder of causation. So mental simulation or imagination has long been debated as to whether it's a form of perception or sensation, and we have found counterfactual reasoning ability in children. For example, they like to pretend play. What is your opinion on how the human mind identifies counterfactual relationships in the world?
I think the human mind has a counterfactual model, has a structural equation model. So I think what I presented here is not divorced from the way that human mind works, because people do answer counterfactual questions. People do exercise imagination, and I don't know of any other model that can, any other computational model that can answer those questions parsimoniously, clearly, except the one that I presented. So I must come to the conclusion, and I might step on some people's toes here, that the neural architecture of our mind is somehow related to the causal models that I presented here. I don't know if I answered you, because you had, I missed some key words in your question. You had some evidence from some field that defy this conjecture?
No, it actually supports the idea. So, and the diagram that you presented also shows a baby crawling up the ladder. So, the conjecture that I was sharing was that children like to imagine possible worlds when they play. This is something that's found through empirical evidence. And yeah, that was what I was suggesting.
Oh, good. So you have only supported my conjecture. Yeah. But something that we still do not know how to process is the question of analogy. I think most of the causal relationships that babies grow up with rely on analogy. babies are growing up with toys and with switches, light switches. So when they are facing with a more abstract problem, they relate it to the expertise they acquire in the crib. This is something that I don't think computer has been programmed yet to do, reasoning by analogy, but I may be wrong. It's a very important component in the early stage of development. And in science too. Analogy plays a tremendous role. Eratosthenes would not have measured the radius of the Earth if it didn't use analogy. According to the Greek, the Earth is round because we are walking on a turtle shell. So if we are expert on turtle, we know the turtle shell has a radius, and that caused Eratosthenes to spend time, a lot of time, to measure the distance between Aswan and Alexandria and figure out the radius of the world. It's something we did not occur to any Babylonian astrologer or astronomer, even though the Babylonians were much better curve fitters than the Greek. But it didn't occur to them that the Earth has a shape and therefore they can measure it. So analogy is a very important part in science as well.
Thank you very much.
Thank you. Yeah, so I think we probably can stop here, and let's thank Yuda again for the great talk, and also thank you for everyone attending this seminar. Thank you.
Thank you all for listening to me.
Yeah, if you have questions, please do follow up with Yuda offline by email. Yeah.
Yeah, anytime. I live here. Great.
Yeah, we are still here. Hey, Yuda. Yeah, great talk. Yeah, thank you for giving the talk in this seminar.